else you say?
I love mathematics.
Again?
I love mathematics.
Good. Now, in this lesson, we're going to be exploring scales. We're looking at scales and before we go on to say what scales are, we think about where we would find scales. Where is it we need to apply the knowledge we have pertaining to scales. Now just imagine we have a diagram of a map. Maybe you have the map of countries in the Caribbean or the map of Guyana. Or you're building a home and your parents want a plan. They have to get a plan before. They just don't go out and buy blocks and buy steel and cement and start building. They have to get a plan. And on this plan, you would see a little key. And it would tell you so many centimeters represent so much. Okay, that's a guide for you to understand the map. Good. Now, the distances on the map is going to be far different from the distances on the ground or the distance on the plan. Maybe 1 centimeter on the plan represents maybe 10 meters on the ground. So every time I see 1 centimeter, I know that's 10 meters on the home. So that's something you need to understand. Now, what really is a scale? We can take this diagram and we can enlarge it. Or we can take the same diagram and we can shrink it or we can reduce it. And when you look at the scale, you see 1 cm to something here. 1 to something. Now a scale is a ratio of an enlargement or a reduction of a map or a plan. Okay? We can increase the size of it or we can reduce the size of it. And it basically identifies a relationship with what you drew to what is it you actually want. So if we're talking about distances, we're looking at a relationship between what is on the diagram to what is on the earth. Like if we're talking about we are here and we want to go to Linden, we can draw a line representing that distance. And then we can measure the actual distance from here to Linden. Or, in the case of a home, we can say, we can look at the little blocks and we can count so many centimeters and we get an idea how big or small the distance is going to really be. Do you need a scale? Do you need a scale?
Yes.
Yes, you need a scale because the scale helps you understand the diagram. Okay? Good. Now, this little scale that you see here can be written in many ways. We can write it as a ratio, or we can write it as a fraction, or we can write it as a statement to say what is it we want to say. Now let us use this diagram again as an example. We say 1 cm represents 100 meters. That's our statement. Now, if we want to say, take the statement and write it as a fraction or in ratio form, the first thing we've got to do is make sure that our units are the same. Here we have centimeters and we have meters. We say 1 cm on the map is going to be 100 meters on the ground. Are the units the same? No, the units are not the same. So first we've got to make them the same. Now we have 100 meters here. Now let us start with 1 meter. 1 meter. How many centimeters will we find in 1 meter? 100. Therefore, in 100 meters, we're going to have 100 by 100 centimeters. And when 100 is multiplied by 100, how much will we have? 10,000 centimeters. So we can now write our scale in ratio form. In ratio, it's going to be 1 to 10,000. As a fraction, it would be 1 upon 10,000. So every time I'm 1 centimeters on the map, I'm 10,000 centimeters on the ground. Every time I'm 1 cm on the map, I'm 10 cm on the ground. Does everybody understand that? Everybody?
Yes, miss.
Good. Now let us take a question. Example 1 across there. 1 centimeter on a drawing represents 10 kilometers on the ground. Every time we move a centimeter on a drawing, we're actually moving 10 kilometers on the ground. Write a representative fraction for the scale. Now a representative fraction is writing it in fraction form. So we're going to abbreviate representative fraction to RF. Representative fraction is equal to the size on drawing divided by the size on the ground, or the actual object. Good? So the ground would be like the earth and the object would be like the home, the actual home you want to build. Now in this case, they say here 1 centimeter represents 10 kilometers. And remember I told you earlier that first of all, you have got to satisfy this condition. Your units must be the same before you can write it in this form. Now we already know the size on the drawing is 1 cm, so we can insert our 1. But then we have 10 kilometers here. So we've got to do some converting. Now we need to know how many cms are in 1 kilometer. In 1 kilometer, how many centimeters do we have?
100,000.
100,000. 100,000. So every time we move 1 kilometer, we're actually moving 100,000 centimeters. We have to move a distance of 10 kilometers. Therefore, 10 kilometers would be equal to 10 multiplied by 100,000. And what would we have there?
1 million.
1 million. And this would be cm. Now that we have cm and cm, we can write our representative fraction, which would be 1 upon 1 million. Any questions?
No.
You see the importance of a scale?
Yes, miss.
Yes. So if you're working with the carpenter and the carpenter tells you 1 cm represents 1 meter, and you imagine 1 meter as the length, and when you're finished he's telling you you're going to have a house of length 10 meters, you know something is wrong when you want a 40-meter house. Okay? So this here would help you when you're ready to do things like those. Good. Now let us look at example 2. On a map, the distance between two towns is 3 centimeters. If the scale is 1 to 15,000, what is the actual distance in kilometers? Let's go it again. On a map, the distance between two towns is 3 cm. So maybe we have a town here, and we have a town probably somewhere there. And the distance between the two is 3 centimeters. At the bottom here, we have a scale which says 1 to 15,000. They want to know now, what is the actual distance in kilometers? Now, we are going to let your brains tickle first before we scribble it on the board. Quickly, let me see what is going to be your approach. Every time I take 1 cm, I'm actually taking 15,000. There are 3 cm on this map. What is it actual? What's the actual distance on the ground? Now I've seen several answers. I saw Miracle has 0.45. What did you get, Jonathan?
Same thing, miss.
What is the same thing?
0.45.
Quincy, what you got?
0.45.
Neon, what you got?
0.45.
Fideli, what you got? Right, now let's reason this thing through. The scale says 1 cm on the diagram would be 15,000 on the ground. There are two towns, 3 cm apart. So if one is 15,000, then a second would be another 15,000, and then a third would be another 15,000. How many 15,000s we have here?
3.
3. And those 3 15,000s will sum up to
45,000.
45,000. Now this is pretty long. What we simply could have done instead,
Multiplied by 3,000.
multiply the 15,000 by 3. Now that's our alternative. So we could have multiplied the 15,000 by 3, and that would have given us 45,000 centimeters. But they want the answer in
Kilometer.
and we know that 1 km is equal to how much cm?
100.
100,000. So if we have 45,000 here, we're going to take this and divide by this here. So the amount in km is going to be 45,000 divided by 100,000, and that will give us, let us go, The zeros will cancel out each other. And we have 45 is being divided by 100. I remember when we did some of our very first lessons, we said when we're dividing by numbers like 10 and 100, we simply move the point. So if the point is here, we're going to divide by 2 zeros. 2 places we have to move. So we move 1, 2. So it's 0.45 kilometers. Okay?
Yes, miss.
Good. Let's try a third one now. We're looking at a model of a barn. You know what a barn is, Neon?
Yes, miss.
What's a barn, Neon?
Place where you keep animals on a farm.
Place where you keep animals and it can be found on a farm. Very good. Now, this farmer wanted a little scale for his barn. And this barn took the shape of a rectangular prism. Let's go. A model barn made to a scale of 1 to 40 has dimensions 50 cm by 30 cm by 20 cm and is in the shape of a rectangular prism. What is the volume of the prism? So that's what we're interested in finding. But before we get down to the volume, there are some other little things that we have got to do. Okay? So, first of all, our scale says 1 cm on the barn is actually 40 on
On the ground.
on the diagram, on the ground. Good? Now, here again, you're saying it has dimensions 50 cm by 30 cm by 20 cm. What is the volume of the prism? Now, I want you to look at that question and study it a little. You attempt it first, and let me see what approach you will take. Trigger you off. So we say 1 to 40. Now we say we have 50. So if we have 50 on the ground, what is the actual length that would correspond to this 50 cm?
2,000.
How did you get 2,000, Jonathan?
I simply multiplied 50 by 40.
So we're going to multiply 50 by 40, and the actual length of the barn would be 2,000 centimeters. Good. Now let us say the width is 30. So here we have the length. Let us take the width now. The width is 30. Therefore, on the actual barn, it would be 30 by 40. And what did you get, Neon?
I go 1200.
1200 centimeters. So we have the length, the width, and let us say this is the height of the barn. And the height corresponds to 20 centimeters. The actual height would be what, Miracle?
800 centimeters.
How did you get 800, Miracle?
I multiplied 20 by 40.
You multiplied 20 by 40 and you got 800. Now if we're going to now find the volume of the barn, that's how much things, or if we should take the barn and flip it over and we want to fill it with water, so we want to know how much it can take. Okay? Good. Now if we're going to be multiplying 2000 by 1200 by 800, that's going to give us a very, very large figure. So what we're going to do, we're going to take our answer in meters. So we're going to convert all of these centimeters here to meters. So first of all, we have to know that 1 meter is equal to how much centimeters?
100.
100 cm. Therefore, 2000 centimeters would be equivalent to how much meter?
20.
20. And that would be 2000 divided by 100. And that would be 20. So we have that going out there. That would be meter. The 1200, same thing there, and that would give us 12 meters. And last of all, here we would have 800 divided by 100 would give us 8 meters. Now we know that the volume of the barn, volume V, would be the length by the width by the height. So let us substitute 20 by 12 by 8. And when we multiply and find the product of 20, 12, and 8, what do we get?
1920.
1920 meters cube. 1, 2, 3. So it has to be meter cube. When it is length, we just have the unit here. Area, we have a little 2 in the power. And volume, we have a little 3. So there we have the volume of the barn as 1920 meters cube. Good? So there we were looking at scales and how we can use them to make life simpler. And if you want to be a person who draw maps to guide people around the place, you need to have a good grasp of the content of scales. Okay, if you intend to be a cartographer. Good? Now, you don't have to be a cartographer to have to understand scale. Just simply wanting to build your own home would empower you with knowledge so that you would not be conned. Right, Alia?
Yes, miss.
You like the concept of scales?
Yes.
Did you learn anything this afternoon?
Yes, miss.
Good. Now let us quickly recap what we did today. Lesson 19, Measurement, Scale. In this lesson, we will use scales to calculate actual areas. Here are some key points. The ratio of an enlargement or reduction of a drawing is known as its scale. The scale of a map or plan defines the relationship between distance on the map or plan and the corresponding distance on the earth or building. There is always a scale printed near a map or plan. Where can we find the word scales? On maps, plans, music, rising or falling pitch sequence, plants, modified leaves, bud scales, Scale, weighing. The length of the line on the map from Lethem to Linden is 10 cm. Linden to Lethem. What is the length on the ground? Scale, 1 to 3 million. 1 cm on map equals 30 km on ground. On maps, scale is represented in 3 ways. 1. As a ratio or fraction, such as 1 to 50,000 or 1 upon 50,000, which means that 1 unit of measurement on the map equals 50,000 of the same unit on the Earth's surface. 2. As a graphic scale, usually a straight line on which distances, most often in kilometers, have been marked off. And 3. As a phrase in words and figures, such as 1 cm represents 100 kilometers. We can use scales to calculate actual areas. A scale that has a representative fraction of 1 to 25,000 can be written as 1 upon 25,000. The numerator and the denominator must be expressed in the same units. Representative fraction RF equals size on drawing divided by size on object. Example 1. 1 centimeter on a drawing represents 5 kilometers on the object. Write the representative fraction for the scale. Solution. The scale is 1 centimeter to 5 kilometers. Representative fraction RF equals size on drawing upon size on object. Size on drawing equals 1 cm. Size on object equals 5 km equals 500,000 cm. Representative fraction RF is equal to 1 upon 500,000. Example 2. How many square centimeters are contained in 1 square meter? Solution. 1 meter equals 100 centimeters. 1 meter squared is equal to 100 cm squared. 1 meter squared is equal to 100 by 100 cm squared. 1 meter squared is equal to 10,000 cm squared. What we did in example 2. Wrote down the scale in ratio form, checked that the units in the ratio are the same, squared both parts of the ratio. The area of a play field on a map is 10 mm squared. If the map has a scale of 1 to 100,000, what is the actual area of the play field? Solution. Scale equals 1 to a million. Ratio of area 1 mm squared to 100,000 mm squared. 1 mm squared to 10 billion mm squared. 10 by 1 mm squared to 10 by 10 billion mm squared. Therefore, 10 mm on the map represents, 10 mm on the map represents 100 billion mm on the actual play field. Summary. On maps, scale is represented in 3 ways. Ratio or fractions. Summary. On maps, scale is represented in 3 ways. Ratio or fractions. Graphic, usually a straight line. and in words and figures. The numerator and the denominator of a representative fraction must be expressed in the same units. Problems for today is taken from Mathematics for Secondary Schools in Guyana, Book 3. It's on page 56, exercise 4E, questions 2 and 8. Solution for the problems given in the last lesson, page 53, exercise 4D, questions 4E, using 3 1/7 for pi, find the area of the shaded part of the circle. Area of circle equals pi r squared. Area of 1/3 circle equals 1/3 pi r squared. That is equal to 1/3 by 3.14 by 31 by 31, which is equal to 1006 cm squared. Question 6. The area of canvas needed to cover the muzzle of a cannon is 50¼ cm squared. What is the diameter of the muzzle? Area A equals pi r squared. 50.25 equals 3.14 by r squared. R is equal to the square root of 16 cm, which is equal to 4 cm. Diameter of muzzle is equal to 2 by 4, which is equal to 8 cm. Question 10. The rim of a wheel has a circumference of 200 cm. When a tire is fitted over the wheel, the circumference increases by 210 cm. How thick is the tire? Circumference C equals 2 pi r. Pi equals 22/7. Let the thickness of the tire equals R1, take R2. When C equals 200 cm, 200 is equal to 2 by 22/7 by R. R is equal to 200 by 7 divided by 44 cm, and that's equal to 31.82 cm. Similarly, 210 equals 2 by 22/7 by uppercase R. Uppercase R is equal to 210 by 7 upon 44 cm, which is equal to 33.41 cm. The thickness of the tire is equal to the uppercase R, take lowercase r, 33.41, take 31.81 is equal to 1.6 cm. So there we go. You were taught the representative fraction, and remember, the units have got to be the same. If you don't want to show it as a fraction, you can write it in the form of a ratio. Or you can put a little statement. 1 cm represents 10 meters. If not, you can have a diagram and show it in a straight line as a graph. There are several ways to represent it.